Hello and welcome to the lecture number 10. So before we going to cover new stuffs, so let me just apologize for a small mistake that I made in the last lecture. So I want to correct that error here. So as we remember that we are talking about the vibration in a two-dimensional membrane, and omega nm is the frequency of the two-dimensional membrane, and it is expressed by velocity pi multiplied by whole root over of this quantity. Now the thing is, if in a special case A is equal to B, then the following equation can be represented as this. Okay, so here now we see the situation for degeneracy arises. So situation for degeneracy arises when? So the situation for degeneracy arises that when we have n square plus n square is equal to n square plus n square. So you understand the point. So that means I am meaning that if n is equal to 1 and n is equal to 2 and if interchange them, so the omega 1 2 and omega 2 1, basically these are frequency wise the same, but their modes are different. Okay, so this is the way how degeneracy appears. It fulfills these two conditions. One is A equals to B, and the second is n square plus n square is equal to n square plus n square. So, but the time if A not equal to B, then the situation for degeneracy would never appear. And here, of course, if n is equal to m, also the degeneracy breaks down. That means it has only one frequency, one mode, and we call them non-degenerate mode. And same thing here, if A is not equal to B, no matter, even if this condition is fulfilled over here, every situation would be non-degenerate. Okay, so that was the little mistake happened during the last lecture. So this is to be remembered, and I have corrected it. So now we are all set to go for the chapter 3. So let's start now. So now we start our foundation chapter of quantum mechanics, that is chapter 3, Schrodinger equation. And here we will learn, my microphone was not connected, so sorry about that. So here in chapter 3, we will learn about the Schrodinger equation of some simple systems. Okay, so in our second chapter, we learned about the classical wave equation of some macroscopic subjects that can be explained by classical physics. So now we can think about that when in quantum domain, atomic or subatomic particles follow quantum physics or quantum mechanics. So there should be an equivalent kind of classical wave equation. So you can think about that Schrodinger equation is something, that kind of equation. So that can govern the movement of or mechanics of subatomic particle. So when we solve the classical wave equation, the solution was what? An amplitude function, okay? U function of x and t. Similarly, if we can solve a Schrodinger equation, the solution is called wave functions, okay? So it is represented as psi, and like uxt, it can be a function of both x and t. All right. So now the thing is, the Schrodinger equation is actually of two types. Okay, so there are two parts. One is called the time independent Schrodinger equation, and another part is of course time dependent. Okay. For the time independent Schrodinger equation, if we solve them, the wave function, definitely these are called psi. So those psi's are only function of x, and then we call this thing as stationary state function, okay, or stationary state wave function, because it represents a stationary state where the function psi is not dependent of time. Okay, and of course if you think about uxt for the classical wave equation, that means the solution for the wave equation, u is an amplitude function, x and t. Similarly, the question is, can we call psi as an amplitude function? Of course, because psi would represent the same properties as of u. Okay, so another name of this wave equation psi, or psi function of x or xt, can be called as an as an amplitude function. Okay, so in chemistry, these time independent functions, that is the stationary state wave function psi x, are of particular interest because this type of solution can explain the different energy states of atoms. Okay, so majorly we will now focus or concentrate on time independent Schrodinger equation. So let's take a look at how Schrodinger could have imagined the development of the time independent Schrodinger equation, from where a stationary state wave function can be found. Okay, so let's move on and let's take a look at this. So now we will try to derive an indirect derive in indirect manner how the Schrodinger's equation for time independent system arises. Okay, so let's try to imagine that how Schrodinger could have conceived the time independent wave function of a particle. In fact, Schrodinger never gave this equation directly, so he had some other equation. So we will come to that later. But first, from a rational basis, let's try to imagine that, okay, so in whether this process of thought, this thought process could have landed Schrodinger to the correct expression. Okay, so for that we have to take the help of, as we mentioned, that the Broy's wave particle duality. So according to his theory, that matters can behave like wave also, means matters that especially matters that follows the quantum mechanics, means the subatomic particle in quantum domain, can have a wave-like property, and therefore it can be associated with a wavelength lambda. Okay, so now let's try to go into the little details of the derivations. Okay, so I need to use the whole board space, so therefore I'm deleting it and I will start afresh. Okay, so let's begin. You can recognize the classical one-dimensional equation. So this kind of equation can be applied on a system of a one-dimensional string attached at both ends. Okay, so this is a confined one, and therefore any disturbance would create a standing wave, and the classical wave equation is this for this system. So now let's imagine and extend the same concept on a quantum mechanical particle, say an electron. So therefore, now you can imagine that this is for the string. Okay, and now we consider the case on an electron. So the string is under some kind of confinement, okay, because both ends are fixed. So how we can extend the thing for the case of electron? So well, what we can think that as if the electron is under some kind of a potential field. So electron, we can think it is under a potential energy. So it has a potential energy U, which is a function of x, means only the position. Now, the electron may or may not have a kinetic energy. We don't know, that is abrupt. But let's imagine that this is under some kind of potential field, potential restrainment, and the corresponding potential energy is U of x. Okay? So, we can imagine that, or we already knew that the solution of such kind of one-dimensional wave equation, okay, it can be written as something like function of x multiplied by cos omega t, provided if we set the phase angle phi is equal to 0. If you are confused how it comes, so you can refer to the equation 2.26 in Macquarie's Viva student edition. Okay, so from there you can relate to this equation. So the amplitude function can be written as something like this when particularly the phase angle has been set to 0. Okay. So now we can think that for electron, the same amplitude function, okay, can be written as this U of xt. If we extend that for an electron, we can now make it as if this function of x is the psi of x and cos omega t. Okay. Now this psi x part, we can call it, this is a spatial amplitude function. Okay. So spatial amplitude function means, as you can see, we have deliberately made it independent of time t. It is only the function of x. So that means that how the amplitude function of an electron is only varied with the position and not with the time. Okay. So now if we can imagine that u in this equation, if the solution, one of the u xt is of this nature, so psi x multiplied by cos omega t. So now you think that this function is a product of two independent functions. Okay. That is a function of x and a function of t. Okay, right? And this is a partial differential equation. So how can we proceed? So definitely, instead of u, we take psi x cos omega t, and we can call it as our equation 2. All right. So now if we can put equation 2 in equation 1 and try to solve it, so let's see what happens. Okay. So let's now try to take the derivative, partial derivatives. So u is a function of both x and t. So when we take the first derivative or the second double derivative of u with respect to x, so cos omega t would serve as a constant value, and we can have this ordinary derivative, that is d2x, d2 psi dx square, okay, is equal to 1 over v square. Now we have to take the double derivative with respect to t, where the psi x would behave as a constant, okay, psi x, and then we have to take the double derivative of cos omega t. So cos omega t, first derivative would land you of minus sine omega t, and therefore omega would come out minus omega sine omega t. All right, first derivative. And the second derivative, again, it would give you omega square cos omega t, and the negative sign will be there. All right. So now you see both ends, we have cos omega t and cos omega t, so therefore it cancels each other out. Or we can write the above equation as d2 psi dx square plus omega by v whole square psi x is equal to 0. All right. Now you see two things. First of all, that you see this equation is independent of time. It cancelled out, all right? And secondly, the form that you see here, okay, it's what is that? This is an ordinary differential equation. And you can call it time independent Schrodinger equation at a very, very primitive form, okay? So now we have to convert this thing into Schrodinger's original equation. So what we have to do? So we have to relate this term with energy, okay? Then only we can define a system. Okay, so how energy can be defined? So the energy E is the summation of the potential energy plus the kinetic energy. All right. Now we have already defined an electron following this equation. We can call it the equation 3. Following the equation 3, having a potential energy U, which is a function of x, of course, plus the kinetic energy. The kinetic energy, definitely, we can write it as half mv squared according to the classical mechanics. And this half mv squared further can be written as p squared by 2m. All right. So now we have this expression. We have a plus sign here. The total energy E is equal to ux plus p squared by 2m. So now here, so we can write 1 second here to make sense. Okay. So at this point, up to this point, everything was kind of classical. Because we did not cross or did not apply the Broy's wave particle duality. All right. So now it is time that we will apply de Broglie's wave particle duality. So according to de Broglie's theory, lambda is equal to h by p. The moment we write this, then actually we come into the domain of quantum mechanics. So we can then express this p momentum in terms of lambda and h. And when we write that, then we can say that quantum mechanical particle behaving as a wave. Okay, so let's quickly do that. So we have got these things so far. That's the equation number 3, and this is the relationship with energy, potential energy and kinetic energy with the total energy, and this is de Broglie's principle. And then we have another part, omega by v. So now let's try to convert this omega by v into something related to this wavelength lambda. So let's try to do that. Okay, so here we can go, then we can do this on the right hand side, that omega by v, all right, so whole square. So this term we need to expand. So omega stands for 2 pi nu. Nu is the frequency, and v is equal to, you remember, nu times lambda. All right. Now everything is equal to whole square. So that transforms into 2 pi by lambda whole square. All right. So here we already have the lambda term now. So through lambda, now we can relate the energy to momentum. How? So here, or we can express p squared by 2m is equal to e minus u of x, or p squared is equal to 2m multiplied by u minus e minus ux, or okay, we can write the p term is equal to root over of 2m multiplied by e minus ux. All right. So now here we will directly apply the wavelength of electron following such system is equal to h by p. So p is here root over of 2m e divided by u of x. All right. So now our ultimate goal is to convert omega by v into in terms of h over energy. So therefore, from this we can write that this is 2 pi, all right, whole square divided by lambda square. So what is lambda? This is lambda. So we can write the lambda square value as here is equal to 2 pi whole square, okay, divided by, so h square part will come here, and here we have to write the top part, right? So the top part becomes 2 pi whole square multiplied by, uh, just a moment. So we can write that term over here. So that becomes 2m e minus u of x. All right. So here further we can write it or is equal to 2m e minus ux. All right. Now this 2 pi square divided by h square, we can bring this 2 pi square term down, so it becomes h by 2 pi whole square, okay? Or in other words, we can also express the denominator as h cross square. So h cross is equal to h by 2 pi. So now what we get the value of that? So we get the value of omega by v whole square is equal to this. So now it's our job to replace this quantity into here in equation number 3. So let's erase the board and let's do it. So if we can expand the value of omega by v in terms of h and the energy, so we can write this thing as d2 psi of x dx square plus 2m e minus ux divided by h cross square psi of x is equal to 0. So here we get equation number 4, and this equation number 4 is nothing but, it is called the famous Schrodinger equation for a quantum mechanical particle, which is electron, which is under a potential energy field, and its potential energy is u of x. And of course, this is called the time-independent Schrodinger equation for a particle under a potential energy field. Okay. So this equation number 4, or the time-independent Schrodinger equation, can be rewritten in a bit different form if we just change this part a little bit here and there. So let's do that. So, or what we can write, we can break this term as 2m and then e of h cross square psi x, all right, minus, okay, once again we can write 2m u of x divided by h cross square psi x is equal to 0, all right. So what I'm going to do now is, right now I am going to take the psi, this energy part, means the total energy part in one side and the other part on another side. So let's quickly take a look. Yeah. So how are we going to do that? What we can do is we can multiply both left and right hand side by h cross square over 2me. So, or we can write h cross square divided by 2me d2 psi x dx square, okay, plus this part is now unity, this part, so psi x minus, again this part is unity, ux psi x is equal to 0. All right. So this looks, sorry, I missed the E part. So the E part should be over here. Okay. Energy multiplied by psi of x. So this is another interesting presentation where h cross square by 2m part only appears at the left, and these are of these terms are free of those is h square by 2m parts. Okay. So now, so here e part will be there. I'm sorry. Yeah. Okay. So this is the form that we have got. So now we would like to do one more step. Okay. So the one more step is I want to write the total energy part on the right hand side, as I have mentioned earlier. So or what we can do is h square by 2m d2 psi x dx square. Here what we write, this minus ux psi x is equal to minus e of psi x. All right. So now you still see that this left hand side is equal to right hand side, but there is a negative part. Okay. Now still I want to do one more simpler step. So I want to get rid of this negative sign on the right hand side. So I would multiply by negative sign to the both sides. So let's do it, and let's write it over here, and let's see what do we get. Okay. So if we do that, so this equation would transform into here. So or we can write minus h cross square divided by 2m d2 psi x dx square plus u of x psi x is equal to e of psi x. All right. So this form is also another form of Schrodinger equation, and we can call it as an equation 5. And that's not all. Once again, the equation 5 can also be simplified a little bit. So how we can simplify a little bit? So or we can make this thing appear okay, so I think I'm gonna stop it here, because in next class we have to learn a little bit of things like operator, etc. And then the further transformation would make sense. So far we can regard this both equation 4 and equation 5 as time independent Schrodinger equation. So remember, we have derived it by assuming that the amplitude, the spatial amplitude function is independent of time for electron, and then only we have arrived at this time independent Schrodinger equation. But that is not the original way the Schrodinger proposed this time independent equation. In fact, Schrodinger proposed a different equation, including both the time dependent and independent part. So in few lectures later, I will go back to that equation. I will show you that how from the original Schrodinger equation, this equation can be derived. Okay, so you study these things from your textbook, and let's stop it here, and we will see you in the next lecture, lecture 11, where we will talk about eigenvalue, eigenfunctions, and simple operator algebra. Till then, goodbye. See you.